Good afternoon, everyone. It's great being here with you. My name is Marco Görgmar, and I'm heading our Data Transformation Artificial Intelligence unit at the BMW Group. So the vision and the mission of our team is to drive and scale business value creation through the usage of AI across our value chain. Now, looking to our products at the BMW Group, we believe that individual mobility is more than just moving the body from A to B. We believe it's also about touching the heart, stimulating the mind. And what you see here is the BMW iVision Circular. It's a compact, all-electric vehicle that shows how a sustainable and luxury approach in the future could look like. And we believe this future is electric, digital, and circular. So today, I have an exciting use case for you where we touch on all three of those areas. And before I jump right into the use case, I just want to give you a short overview of where we stand with our data and AI transformation. So we have built up a data analytics and AI ecosystem at the BMW Group, and we had more than 40,000 of our employees engage here. And they created thousands of curated data assets in the company that can be reused and brought siloed data together. And based on this, they were able to deliver more than 800 use cases with more than $1 billion value since 2019. So we're taking this transformation very seriously, and one main area where we focus on is sustainability. And today, I want to drive you through one specific area there, namely urban mobility. So around 60% of the world's population lives in cities and urban areas, and that's also where 70% of greenhouse gas emissions are generated. So clearly, we can make the biggest contribution here, and that's why we, the BMW Group, are getting involved here. And our vision and also the idea is here to assist city planners in solving problems in those urban areas. And let me give you 3 examples how we do this already today. So we're able of training machine learning models to predict how new traffic regulations, for example, e-drive zones, can favorably reduce traffic and gas emissions locally. We can also help identify where we have insufficient charging infrastructure, since obviously that prevents people from switching to an electric vehicle. And the last example here, based on machine learning models, we can predict how change in pricing policies, for example, for parking or use in certain streets, can impact drivers' commuting routes and therefore estimate the traffic and emission. So, and all of these problems, they're characterized by geospatial information. So to solve them, we had to extensively use geoservices within machine learning, such as map matching, efficient geohashing, or digital maps. And we opted to test the new geospatial capabilities Bratin just mentioned, and let's see how and with what results. So specifically for our fleet customers, so large company fleet, it's difficult to foresee how their share of electric vehicles will look like in the future. So we set us the goal to train machine learning models to learn correlations between engine type and driving profiles. The rationale behind this was if such a correlation would exist, then the model could learn to predict the affinity of certain drivers for an electric vehicle based on their profiles. Of course, we did this with fully anonymized data and also only on a fleet level, so we could never draw any conclusions to individual drivers. So now let's see how the solution works. So we started from anonymized raw GPS data of where vehicles are driven and parked. And then we converted those GPS traces into routes using map matching. And if a route were a sentence, then the landmarks along the route would be words. So we used a natural language processing model to predict which routes are likely to be taken by EV drivers. In parallel, we built a second model to cluster vehicle parking locations to predict where EVs are likely to be parked. So, for example, near charging infrastructure. Then we merged the 2 models to triangulate the predictions, and at the end of the training, the hybrid model was capable of predicting how likely it was for specific fleets to convert to EV with an accuracy of more than 80%. So let me show you 3 things that really helped us here to be so quick on building the solution. So one advantage of SageMaker geospatial capabilities is the standardization of common APIs to access, transform, and enrich geospatial data. So, for example, for reverse geocoding, SageMaker provides a single managed interface to APIs by the integration with Amazon Location Services. And they, again, source high-quality geospatial data from Esri and here.com. So second thing is, with SageMaker, you have pre-built algorithms that split the raw data set along geospatial boundaries, so the data can be used for training and inference. And in the end, of course, you need to visualize. And there are great pre-built visualization tools really tailored to geospatial data. So to sum it up, yeah, we went from idea to solution in just 8 weeks. And with a high accuracy of 80% in prediction in that short time. So it was really great using the services, and they helped. But we also had a great collaboration with the Amazon Machine Learning Solutions Lab team and our internal BMW team. So Bratin, thank you very much for the great collaboration.